Morning, everyone. Thank you for coming to the class. Sorry again if I missed Wednesday lecture. There's a technical issue with my Zoom, and I was also in a meeting. I couldn't quickly cancel the other meeting and jump back to the class. When I was trying to do that, there's some disconnection on the software, so I couldn't make it work at the time. So sorry about that. So we missed one lecture, but we should be able to catch it up through today's lecture. And again, once you join, please mute yourself unless you have something to say. So this way we don't have a lot of noise, background noise interruption. Okay. And I believe you all should have finished the homework by today midnight. If you haven't done that, you still have time. And also, if you have questions, you're welcome to stay behind. I can help answer them as we go through the homeworks after the lecture. Okay. All right. Okay. Before I start, there's any general question for me from previous lecture or homework, anything like like that? Anything
Hey,
from me?
Professor,
Yes, sir.
are we expecting to get done early today? Because I have a event at 4 o'clock your time that I have to be at.
4 o'clock, right? I don't think we'll get that far. I mentioned that before. Usually for Thursday lectures from 1 to 2:30.
Awesome, thank you.
Yeah, sure. Thanks. Okay. Alrighty. So any other question for me, ladies and gentlemen? Are we all good? Okay. So now let's, without further ado, let's quickly jump back to the lectures. So again, I'm going to share my notes and you should be able to see it on your screen. And if not, let me know. Okay. So this is my screen. All right. A quick recall what we have talked about last lecture, right? What we have talked about last lecture. So last lecture we talked about, so recall bending. Okay, this is, sorry, this is a little bit too thick. Let me change it a little bit. So this is better. So bending of, so review, bending of RC beams. Okay, so we talk about if I have a beam that is reinforced concrete beams, right? So it follows a shape like this, all right, and it bend like this. Okay, so if I make a cut here in the middle section, and mind you that this is so-called constant moment zone, all right? It's constant moment zone. So I end up with a segment on the left like this, and this is my moment. And on the cut, I have a counter moment goes this way, right? So on the section here, I will have, on the section here, I have compression from the concrete, I have tension from the steel, and I have a distance in between. I have a distance in between. And the moment here should equal to either tension multiplied by the distance or compression multiplied by distance, right? They're the same.
Hey, Professor.
Yes, sir.
So there's people in the waiting room trying to get on the
Oh,
Zoom link. I don't know if that's
yeah,
something you can change or what.
I already did that. Yeah, sorry. I think it was delay. Yes.
بس بقول لك يعني الموضوع
Thank you for remind me. Okay. And again, for those of you who just joined, please mute yourself so I don't hear my own echo, background noise. Thank you. All right. So this is the internal force equilibrium, right? So it's pretty straightforward. Pretty straightforward. And then we also would like to take a look at the cross section, right? Cross section. So we say in a typical cross section, we're looking at a rectangular section like so. We have two bars at the bottom, and we have reinforcement. Okay, stirrups, and we also have the dimension of the section. The width is b, height is called h, and also introduce a new concept that is distance between the top of the section, top fiber of the section to the center. Be careful, okay, to the centroid of the last layer of reinforcement. Okay, last layer reinforcement. This is called the depth d. Okay, since I only have one layer, all right, since I only have one layer, so I just have D. Okay, we'll talk about more details if I have multiple layers. right? If we have multiple layers. But this is the definition of depth, right? So we call this, since it's only one layer, and well, I wouldn't say it's only one layer, but since I only have one side of reinforcement, that is the reinforcement is at the bottom or vis-a-vis in the tension side, we call this section singly reinforced section. Okay, so singly reinforced section. Okay, be careful. This singular reinforced section, the word singular has nothing to do with single layer, only has something to do with that I only provide the tension reinforcement. So you can also say tension reinforcement only. All right, that's the equivalent term of singular reinforced, because we'll talk about a double reinforced later, which includes a compressive reinforcement. All right, okay, so extending the neutral axis line, extending the neutral axis line, and I want you to remember this because you need to draw this strain distribution, stress distribution, internal force distribution in your homeworks and in the exam because you receive partial credits, okay? You receive partial credits, okay? Of course, now doing so, 0 point, right? So if you have a strain on the top of the fiber at failure, this is always going to be epsilon Cu, and knowing that this number is 0.003, all right, 0.003. And then I draw the section right here and extending the bottom line here, and knowing that this neutral axis, right? Recall definition of a neutral axis, meaning no strain, zero strain, right? So extending that straight line to the bottom here, crossing at a value of epsilon s, which is at the level of steel, okay? This is epsilon s. This is epsilon, and make sure that this epsilon s is always greater than the yield strain epsilon y, okay? Always greater than yield strain epsilon y. So that is, make sure it yields, okay? And we call this diagram the strain diagram. We call this strain diagram. So that I need to make it thinner so it'll be easier to see it. So this is called the strain diagram. All right, now if I draw the actual stress distribution, remember, if I draw the actual stress distribution, and we have talked about this, we say because the stress in the compression side is too complicated, right? I'm going to use simplified stress distribution. So what simplification? The simplification goes with so-called Whitney stress block. So the Whitney stress block says I will have an equivalent distribution of a block having a strength of 0.85 F prime C. All right, and I also have a length of that block, okay, length block. Now this length block is called A, and it's a discounted actual compressive zone beta 1 C, where C is the actual compressive zone right here. Okay, so A equal to beta 1 C. A equal to beta 1 C. Now, correspondingly, I have a tension here on the tension side, and you may ask, oh, what happened to the concrete and tension side, Bob? Well, the concrete cracked, right? Has nothing left, no residual strength. All right, so the only thing left is the steel in the tension side, and let's call the stress in the steel Fs equal to Fy. Why? Because it yielded. Okay, so this is called the stress distribution. All right, stress distribution, and you should remember that. Now keep extending the line, and now let's take a look at the internal forces. So I'm going to draw the section again. Now I'm going to use red to represent the total force, right? From concrete should be sitting right in the middle of this block here, right? So this will be the concrete compression from the concrete. And we know that distance between the top fiber to this compression force is A over 2. Now the corresponding tension side, of course, I only have a tension from steel, and this is T, which is AS, area of steel, and yield strength of steel Fy. Okay, and now the distance between the compression and the tension side here, this equal to what? The distance is JD, by the way, lever arm, and that equal to a D depth minus half A. Okay. All right. So now this is all we care about actually in the reinforced concrete beam. All right. So this is what we talked about last time. So let me zoom out and draw a division mark here. Okay. So what is the discussion today, right? Lecture 2. What are we going to talk about today in lecture 2? So we're going to talk about analysis, okay? Analysis of single layer, okay, comma, single layer reinforced. And remember, what does singular reinforced mean? Only tension reinforcement, right? Single layer reinforced RC beam, okay? Or MN. Need to calculate MN, moment capacity. All right, that's what we're going to do today, okay? So now we have the stress distribution, right? I want you to pay attention at this fellow here. So I'm just gonna copy this block. You can either do the same, or if you have trouble doing that, don't need to worry about it. I'm just gonna put it as a reference. I'm not gonna really use that a lot. It's just you can see it, okay? So we already analyzed this. Right? We say that in this, what we call the internal forces. By the way, I forgot to label it, okay? So put it here. This is called internal forces. Internal forces. All right, so please follow me. Just do a quick check, right? So I have section, strain, stress, and internal forces. Make sure you have these 4 miniature figures drawn in your homework and in exam, and I will give you at least 20% of partial credits, okay? At least 20% of partial credit. That means even if you forgot how to perform the rest of it, as long as you show me this diagram similar like this and has to make sense, I'll give you at least 20% partial credit, okay? Very important, valuable, right? This is even better than lottery, right? This is a short thing, okay? All right, so coming back quickly. So this is internal forces, right? Internal forces. Observing the internal forces, we have equilibriums, right? So equilibrium on the section demands that my compression got equal to tension. Isn't it? And in the last lecture, we talked about this. We say the concrete compression equal to 0.85 F prime C A, which is this area, and multiplied by B, which is the width. And if you forgot where the B coming from, you can review last lecture. We showed you a 3D drawing. Where's the volume, right? Where's the width of the section, and you got a volume here, okay? So that is the total compression, and we have to let this equal to the tension, which in this case, ASFY, okay? ASFY, and that equal to the tension force T. All right. So this is miraculous, right? This is good. Why is that? Because now I can rewrite the equation into A should equal to ASFY divided by 0.85 F prime CB. So if I know my area of steel, sorry, excuse me, and the grade of steel, which is the yield strength of steel, concrete compressive strength and the width of the section, I can compute my so-called A, which is another term here, effective compressive zone. Okay, very important terminology. Need to remember this, okay? Effective compressive zone. Okay, effective compressive zone. All right, and now once I computed my effective compressive zone, I can even go further because now I can compute my actual, and see this is called actual compressive zone. Okay, and that equal to A divided by beta 1. And we have talked about beta 1, right? Beta 1 is a concrete dependent coefficient. Remember, beta 1 value here is dependent on the compressive strength of concrete at prime C. As 2 magic number, 4 KSI and 8 KSI. If it's below 4 KSI, we have a 0.85 in beta 1. And then if it's Beyond A KSI, I have 0.65 for beta 1. And in between, remember, we just connect a straight line and do linear interpolation. Do linear interpolation. Okay, so now this is actual compressive zone. In a sense, what is the C, right? What is the C? Remember, in the actual compressive zone, we go back to the strain distribution diagram. Strain distribution diagram, this is epsilon Cu, and now that is the actual compressive zone C. Okay, so some of you may start asking questions, why do I need that? Why do I need actual compressive zone C? I mean, for all I understand, I need to get effective compressive zone A. I can compute, right? I'm happy with it. So why do I need actual compressive zone C? You need it because remember, all this was under the assumption that, I'm sorry, I have to stop for a second. Just give me 1 second. Sorry, just went out a little bit. So here, continue. So we have this strain diagram. We know the actual compressive zone C. And the reason we need to know that because before we did all this, right, we were assuming epsilon S, remember, is bigger than epsilon Y, which is yield strain. For grade 60, you can safely assume this number to be 0.00207. But this assumption, remember, this is assumption, remember? So we have to be able to find epsilon S and confirm this, right? Confirm this to utilize all this witness stress block, okay? So that's as a confirmation. So how do I find epsilon S? You use the similar triangle thing, right? So this is depth D, remember? This is depth D. So use the similar triangle. What kind of similar triangle, right? So you have a triangle here, all right? And you have a triangle here, right? So you can use that to get your epsilon S. So uses the relationship, the strain in the steel epsilon S would equal to bracket inside the depth minus actual compressive C divided by actual compressive C and multiply epsilon Cu. Okay. That is how we calculate the epsilon S. And once you get this strain epsilon S, okay, and we just have to make sure that is bigger than the yield strain epsilon Y, and epsilon Y is equal to the yield strength Fy divided by Young's modulus of ES, right, of the steel. And just so you know that, remember, Fy for grade 60 is 60 KSI, and Young's modulus for steel is 29,000 KSI always. So this gives you a rough number of 0.00207. All right, 0.00207. So all we have to ensure is this holds, okay, to be able to do analysis like this. And you say, why? Because all analysis we have done was under the assumption of what? To ensure we could use witness stress block, okay? So very critical, okay? So you have to make sure that your strain is still yielded larger than the yield strain of the steel to make sure you can use the witness stress block, all right? So once we make sure of that, right, the moment capacity becomes very easy. So the moment capacity Mn, and mind you that there's another term for it in case you were wondering about the textbook and the design code ACI. This is so-called nominal flexure capacity or nominal moment capacity, or resistance. There's so many words, right? But it's just nominal moment, right? So N representing the word nominal, right? Nominal. And you will say, why nominal? Now we talk about there's a strength reduction factor, right? We talk about that shortly. But this is called the nominal moment resistance, okay? Nominal moment resistance. And to compute that, we say that equal to a tension, right? Multiplied by JD. And turns out this JD in this single layer reinforced section happened to equal to D minus half A. Okay, and also equal to CC multiplied by D minus half A. And to write it out, right, don't forget tension T equal to AS Fy and compression C equal to 0.85 L prime C AB. So you can either write mm equal to ASFY multiplied by distance d minus half a, or 0.85 f prime c a b d minus half a. Now, whichever way you want. Okay, whichever way you want. All right, so this is mm. It's called nominal moment resistance, or you see from other texts called nominal flexure strength. Okay, I will try to restrain myself to calling it only nominal moment resistance. But if you see nominal flexure strength, don't be alarmed. They're the same thing. Okay, they're the same thing. They are the same thing. All right. Okay. All right. So this is the analysis procedure for a single layer, singly reinforced RC beams. Right? So let's quickly review before we move forward. So we want to utilize compression equal to tension. So directly we utilize this equation here. So this is called step one. Step one to find compressive zone, right? So to find A or find A and C, okay? So this is step one. And that is the equation used for step one, okay? To find A and C. Now, once we find A and C, and step two is to find what? Step two is find epsilon strain is yielded, right? Strain is yielded, and use this equation right here. And step three is to find the moment capacity mm, utilize this equation right here. Okay. All right. Okay. So this is how we go on about this business, right? This is how we solve the problem. Okay. But now you see that this whole thing was established based on the important key concept that the strain in the steel has to be greater or equal than epsilon y, right? And what if this is not the case? What if this is not the case? Okay, so I want to introduce another concept today. Okay, this is called a balanced. Okay, critical. It's called a balanced condition. Okay, and this balanced condition is usually related with strength reduction factor. Okay, and that is phi. Right. So balance condition. What is this balance condition? Right? So let me just draw this section out again, okay? Let me just draw the section again. So I have a 2 bars at the bottom here, okay? And I have a width B, height H, and depth D, okay? And I do my strain diagram just like I did before. And I know that failure, concrete always fails at epsilon Cu, which is again 0.003. All right, you should have this number drilled in your head by now. If not, start drilling it right now, okay? And then extending it to the bottom of it, and you find out that if this is neutral axis and my strain condition looks like so, then this is neutral axis, okay? And now there is a critical condition, okay? There's a critical condition. What is this critical condition? That is, what if at this point, what if my epsilon s, which is the strain at last layer of the bars, happen to equal to epsilon y? Happens to equal to epsilon y. Okay, so if this happened to equal to epsilon y, and we call this the balance point, all right, balance point. Okay, meaning that the strain in the last layer of steels, because naturally you may have, right, you may have layers here, you may have layers on the top, so on and so forth, but last layer, right, last layer of steel has a strain that happen to be epsilon y, and this is called a balanced point, all right, balanced point. Okay, balanced point. All right, now if this is the case, right, if this is the case, if I have the other cases where let me use a different color so you see better. So if I have another line goes this way, so naturally at this case, my epsilon s is greater than epsilon y. Okay, greater than epsilon y. And this case, we call it under reinforced. under reinforced. Okay, meaning that the reinforcement is not too much. It's good. It's just okay. So that I end up with my steel yielded at failure. Yielded at failure. However, though, if I have to have a different case that maybe my strain is, in this case, sorry, here. In this case, my strain is smaller than yield strain, means my reinforcement is not bigger than the yield strain, right? In this case, we call it over reinforced. Too much. Over reinforced. Okay, over reinforced. All right, and you may start asking questions. So Bob, you mentioned that only when the steel yielded can you use the Whitney stress block. Now you have three scenarios. So what's happening? What's happening is that we're still going to use the Whitney stress block, but we're going to use a stress reduction factor to reflect these different conditions. Okay, different conditions. But before we do that, let's get the numerical value out of it. Now, let's talk about these three conditions, right? So first of all, let me use the right color so we can color code it correspondingly. So first of all, balanced condition, right? Balanced condition. Okay, and this is just the terminology, right? Numerically, what does it infer? It infers that when epsilon s equal to epsilon y. All right, and when this happens, I have compressive zone. This is actual compressive zone balanced, okay, divided by the compressive strain epsilon Cu should equal to the depth divided by epsilon Cu plus epsilon y. Epsilon Cu plus epsilon y. All right, and now I can even push further. I can compute that. So this balanced compressive zone equal to epsilon Cu divided by epsilon Cu plus epsilon y multiplied by d. Now let's assume epsilon y equal to 0.00207, or in another word, grade 60 steel. Okay, I essentially have balanced compressive zone. Okay, divided by the depths, roughly equal. This one is 0.003 because that's epsilon Cu, and the 0.03 plus 0.00207, and this approximately equal to flying here, equal to a 0.6. Okay, 0.6. And this is the balance condition. Now, this is a little bit awkward, so let me just move it down here. And don't worry, you don't have to, but it's just for my purpose, okay? So I'm just gonna cut it and paste it here. Paste it here. Okay, and then draw a division line. So we talk about this is a balance condition, okay? But perhaps let's just put it in the middle so see better. Okay, so this is so-called a balanced condition, right? Balanced condition. Now let's take a look, right? If it's a under reinforced, right? Same thing holds, right? So this is when epsilon s bigger than epsilon y, larger than epsilon y. Okay, so I'm just gonna copy all the equation down here, but end up your under reinforced actual compressive divided by d roughly should be smaller, okay? 0.6. Okay, then another thing, last but not least, is what we call it over reinforced condition. And when that happens again, this is when the strain of steel is smaller than epsilon y, meaning it's not yielded, right? Not yielded. And all the way back here, the compressive zone for over divided by d should be bigger than 0.6. Bigger than 0.6. All right. So now there you go. That is the three corresponding conditions, and how you say how it was decided. It's all coming down to the strain in the last layer of reinforcement. Strain in the last layer of reinforcement. Okay. All right. So now this is so-called the three conditions, right? Three conditions. Now let's then talk about the strength reduction factor. Strength reduction factor. Okay. Now the strength reduction factor, and we use that quite often, called phi, is dependent on these conditions. Okay, it's dependent on the conditions. So it's dependent on whether epsilon s is bigger than epsilon y or not. Okay, I'm gonna make a differentiation here. Okay, now epsilon s is the strain in steel. Epsilon s definition is the strain in group of steel. Okay, now epsilon t is the last layer, bottom layer. Sorry for my writing. Last layer of steel. Now for a single layer, they're the same. For multiple layer, they're not the same. All right, but how to show this is that if I have a section, okay, and I have, say, group of bars like so, okay. Now the centroid of these bars, and we'll talk about centroid of these bars has a depth of ds, okay, and we define the depth of the last layer of the bars called dt, okay, and the strain is correspondingly epsilon t and epsilon s. All right, that's the definition. So based on the three conditions, right? Three conditions, the strength reduction factor changes as well. Okay, so we define a strength reduction factor phi, okay, and horizontal axis will be epsilon t, which is the strain, the last layer of the bars. All right, now if this epsilon t equal to 0.002 or smaller, okay, we have one set of value of phi. Okay, one set value of phi. And now if this value epsilon t is around 0.005 right here, we have another set of phi. And this value right here, phi equal to 0.9, and this value here, phi equal to 0.65. And in the middle, again, we do linear interpolation, means straight line, okay? Straight line, okay? And now in this tricky business, right? In this session here, we call this, let me use a different color coding. Remember, we call this under reinforced, right? Under reinforced. Okay, and we call this balanced point. Okay, balanced point. And we call this, let me make sure I use the right color. Under reinforced is, okay, so this is over reinforced. Okay. All right, so that is how we correspond to the three conditions we just talked about, okay? Three conditions, we just talked about it, okay? And this is how we use under reinforced and over reinforced terminology. But ACI has a different set of terminology, okay? ACI basically says, you know what, this is a little bit more complicated to me. So I'm just gonna call under reinforced, right? Under reinforced a transition divided in three zones. So ACI said, you know, I'm just gonna divide this into transition zone and tension control. Okay, so that's where the 0.005 taking into place. Okay, so ACI says, I'm just gonna, and by the way, this is in ACI section 9.3.1. You can find it from your code. ACI says, I'm just gonna divide my under reinforced condition to two zones. One is called transition zone, where epsilon t between 0.02, 0.05, and I'm going to call another zone tension controlled when the strain of steel is bigger or equal than 0.005. Okay, bigger than 0. So let me just write down. So this is epsilon t between, and this is my mathematical between mark, okay, 0.002 and 0.005. Okay, this is epsilon t between 0.005 and above. Okay, and now if it's between 0, if it's between 0 and 0.002, okay, and I call this compression controlled. Okay, compression control or overlay reinforced. All right, you can see corresponding to the color mark. Okay, color coding. Okay, I call it compression controlled. All right, and you may say, okay, all right, Bob, you keep dividing zones. I'm a little bit lost here. What are you trying to do here, right? So what I'm trying to do here is that eventually ACI says the strength reduction factor, which is this red line here, follow the equation of 0.65 plus epsilon t, which is the strain in the last layer of steel, minus 0.002, okay, and multiplied by 250 divided by 3, all right, and this is the equation itself, ACI 9.3, right, 9.3, and then this value here, phi equal to what? Simply, or I can write this way, phi equal to 0.9, okay, when epsilon t is bigger than 0.005 ops. And this is called the tension controlled case. Okay, and has to equal to 0.65, okay, and this is epsilon t smaller than 0.002, and this is compression controlled. Compression controlled. And last but not least, what if your strain epsilon t is in the middle, and that is the transition zone we just talked about. Use that equation there, and this is when 0.02 smaller than epsilon t and smaller than 0.05, and this is transition. All right. So as you can see that it's all coming down to the strain in the steel. It's all coming down to in the strain in the steel. If yielded, right? If yielded and just barely yielded, right? It's in the transition zone. If yielded a lot, bigger than 0.05, it's tension controlled. If it's not yielding at all, it is 0.65 strength reduction factor, it's compression controlled. All right, so final point, right? So you may ask, Bob, you introduced this concept, nice. So I know now there's a strength reduction factor, but how does that ever affect our computation for moment resistance? And specifically Mn here, remember? Mn, okay? This is how it affects. Based on the strain in the section, you will select the corresponding phi and you multiply that in front of Mn and compare it to your design moment or factored. And some of you may ask question in the homework, this is the factored. Okay, why you're confused? Because we also call it ultimate. And I know there are so many names, right? Tomato, tomato, right? So many names. So this is how we use strength reduction factor. And matter of fact, this is the step. Oh, this is step, last step in analysis. Let me see, where is it at? Step 3, so this is step 4. Okay. Okay. So that is, once I computed my Mn, I still need to go back to check my epsilon t, and judging where the epsilon t is at on this curve, use the corresponding function to find phi, and multiply phi in front of Mn to get my actual moment of resistance, okay? And now this phi Mn has another term, endless term today, huh? Another term, and this is called design. This is called design moment resistant. Okay. All right. Or design flexure strength. Either way. Okay. Okay. And this factored, okay, also can be called applied I know this separation mark causing trouble. So also called applied moment, or sometimes you see people call it target moment, so on and so forth. Okay. All right. So all in all, our design or our analysis, the purpose of that is to ensure my design moment resistance is always greater or equal. Sorry, I forgot the equal sign. Greater or equal than mu, which is the factor moment. Okay. All right. Okay. So now at this point, we have concluded all the analysis procedure for compute the moment capacity of singly reinforced single layer reinforced concrete beams. Okay, mouthful of words. All right, mouthful of words. But basically that's it. That's all you need to know. It's a little bit long, but this is what it is. Okay, let me see. What is MU? MU is applied moment. Okay, or factored moments. If you see from homework number 1, that's what you're looking after. Okay, that's what you're looking after. All right. Okay, I want to take a 1-minute pause and ask any questions. There any questions for me on this? Anything? Folks, you fall asleep? Any coffee? Wake up? Any question for me?
We're good.
Okay, you're good. All right. Okay. So,
Good too.
okay, thank you. Just make sure you are listening. I understand this is all boring, long, tedious, and probably meaningless, right? Old concept, right? Old concept. Bob, you keep talking, yada, yada, yada. I don't know what you're talking about, right? Just equations. All right, spare me, right? I can read it myself. Okay, so how do we apply that? Yes, and I have another question here from a chat message. Sorry about that.
Chat asked where step 3 is.
Okay, step 3 is right here, is to find the moment capacity Mn. This block, can you see it?
Yes.
Okay, got it?
Yep.
All right, good deal. Sure, no problem. Okay, so now let's take a look at an example, right? That's all we're here for, example. So example number 1. Okay, example number 1. Okay, compute the nominal moment resistance of a, be careful folks, okay, single, my write up today, single layer and singly reinforced RC beam. Okay, and the cross section is given. All right, the cross section is given. What does it look like, right? The cross section look like just this, a rectangular section, nice and easy. Sit here, has a width of B equal to 12 inches. Okay, and have a height of H equal to 20 inches. Now I have bars, and let's just say I have one row only, 4, okay, 4 number 8 bars. Right, 4 number 8 bars. And now I also know that the distance between the centroid of these bar, the row of bars, to the bottom concrete is 2.5 inches. Okay, so what does it tell me? What does it tell me? It tells me that the depth of the section D, which also in this case equal to dt, is about, wait a minute, where is this t coming from? The t coming from all the way here, remember? Is the last layer of the bars, right? I only have one layer, so that is indeed the last layer, and that equal to d. Okay, and the number is h height, remember, minus 2.5 inches give me 17.5 inch of depth. Okay, and the input parameter concrete compressive strength is 4 ksi, raw ready mix, and yield strength of the bar 60 ksi. Okay, 60 ksi, or in the exam, I will be playing clever. I only tell you it's grade 60. Go figure yourself. Okay, and then the question is, what is my phi mn? Okay, so first of all, let me do this. What is my mn? Okay, moment capacity. Moment capacity. Okay, and be careful. This is nominal moment resistance. There's no phi in front of it yet. Okay, and the next question is, what about phi? Okay, what about phi? All right, so this is the question at hand. Okay, so start solving it, right? So solve. Okay, now I want to go from several steps. So first step, right? I want to find out what is the steel, right? What is the area of steel? I have 4 number 8 bars, okay? And for number 8 bar, each bar have an area of 0.79 inch squared. If you forgot, please find table A5 in your textbook. Okay, table A5 in textbook. Okay, and this is number 8 bar. Each bar 0.79 inch squared, and I got 3.16 inch squared of a total steel. Now, immediately I can start compute the tension force generated from this, and that is 3.16 inch squared and multiplied by 60 KSI. And again, this is because it's grade 60, so I have 190 kips. Okay, and that's my 9. Okay, you get used to it. All right, 190 kips or tension force. All right, so that's the first step. The second step, I want to find my actual compressive zone A, which equal to beta 1C, and that equal to ASFY divided by 0.85 F prime C B. All right, so bring the number in. This is 190 kips on the top. Bottom here, 0.85 multiplied by 4 KSI multiplied by 12 inches. 12 inches, and I have a 4.66 inch. Okay, so that's my actual compressive zone. All right, so immediately in your head, you started seeing, and this is where the partial credit started to count. Okay, this is where the partial credit started to count. So I will quickly draw the section, and I see the 4 bars nicely, and now I show that the strain distribution looks so. This is epsilon Cu. And also I know the stress distribution look just like this. And mind you that neutral axis right here. Okay. And this is compressive stress. And I know this is 0.85 F prime C. And this is A. Okay. And I have a tension right here. So I only have a group of tension right here. You can draw the other side if I don't mind. Okay. So there will be opposite sign here. But this is tension. So this is ASFY. Okay, and that is C, compression force. Okay, so if you draw this, might as well just draw C here, and this is epsilon S. Okay, and you say this is section, this is strain, and this is stress. Okay, and I want to even put more. This is internal force position. Okay, JD equal to D minus half A, and this is internal forces. Okay. So this little bitty 4 figures give you 20% of credits, okay? 20% of credits, okay? Boy, this is kind of like a hot sale, right? Don't miss out on this, okay? Remember to draw these little figures, all right? Okay, so I have these figures drawn, right? I have my actual compressive zone A equal to beta 1C equal to this. And remember, I need to check the strain in the rebar, right? So check epsilon S. So to find epsilon S, I need the actual compressive zone C equal to A divided by beta 1, and A equal to 4.66 inch divided by beta 1. Oh boy, what is my beta 1? What is my beta 1, folks? So draw the drawing. This is F prime C, this is 4, this is A, and by the way, this is the KSI. Okay, so I'm just gonna put this unit here. Okay, for an A KSI. And beta 1 equal to 0.85 equal to 0.65 and straight line in between, right? Now we have what? F prime C, 4 KSI, woohoo, right there, right? So beta 1 immediately equal to 0.85, clear and day, right? So C equal to, oh, sorry, I already have it here, apologize. C equal to 4.66 inch divided by 0.85, and I got C actual compressor zone equal to 5.48 inch. All right, pretty good. Okay, why this is pretty good? Because immediately I can compute my epsilon s equal to depth minus actual compression c divided by c and multiply epsilon cu. So this number depth now is equal to 17.5 inch minus 5.48 I just got and divided by 5.48 and multiply epsilon cu. And you need to remember this epsilon cu 0.003. So I got this epsilon value here as here equal to 0.00658. Okay, 0.00658. Okay, you say, what am I going to do with it? This is what you're going to do with it. First, I need to check my yield strain. All right, epsilon y equal to fy divided by es. And since it's grade 60 is roughly 0.00207. Okay, so immediately you say, bingo, epsilon s is bigger than epsilon y, so yielded. Crap. Yielded. Yielded, right? Excellent. But even better, right? Epsilon s equal to a 0.00658 is actually bigger than 0.005. This is even better because it's tension controlled. Okay, tension controlled. What does it mean? Because now if it's tension control, I draw a phi, and this is epsilon t, isn't it? You say, Bob, this is epsilon s. Did you misread? No, I did not, because I have only one layer, so that equal to that. See, conveniently, that equal to that. And now, immediately, I know this mark is 0.02, and this is 0.005. For 0.02, I know phi equal to, oh, sorry, reversely. Phi equal to 0.65. For 0.05 or above, phi equal to 0.9. And in between, linear interpolation. So where are we at? We are somewhere here, right? 0.00658. So definitely a 0.9. So immediately I say, now, you know what? Phi got equal to 0.9 because it is tension controlled. Tension controlled. Okay. All right. Now, this is actually step 4. This is step 4. But anyway, so let me finish step 3. So Mn, which is the nominal moment capacity, equal to what? ASFY. I'm using this equation because I feel it's simple. Okay. Multiply d minus half a. So bring the number ASFY, which is 190 kips. Okay. Now multiply the depth of the beam. Depth is 17.5 inch. All right, minus actual compressive zone. Be careful, this is A, all right? This is not C. So A is actually 4.66 inch and divided by 2, okay? And you calculate this out and you got 2,880 kips inch. All right, kips inch. All right, that looks a pretty good number, but I want to convert it into 12,000 kips, 12 actually. I want to convert it in 12 inch per foot, convert back to foot. So I got this number to be 240 kip foot. So that is my, don't forget, nominal flexure strength or nominal moment resistance. Okay, nominal flexure strength or nominal moment resistance. Okay, and I also know the design is equal to phi mn, which is 0.9 multiplied by 240. Okay, and that gives me a 200, I believe. Sorry, 216 kips foot. Can somebody double check on me? Did I get the right number, folks? Anybody? Did I calculate it wrong?
Looks all good to me.
All righty, looking good, thanks. Great. So now this is called the design moment resistance or design flexure strength. I want to use flexure strength because I know Dr. Snee like that. So the ACI code also mentioned like flexure strength. So I just want to be consistent. Myself, sometimes I use moment resistance a lot. Okay. All right. But okay, ladies and gentlemen, that's all. That's all. That's all. Okay. That's how we calculate the moment capacity. How we calculate moment capacity and design moment capacity following the procedure. Okay. Following the procedure. So it's not that complicated. You see, it's not that complicated. Okay. All right. But this is easy, right? This is for what? This is what we call the single layer, singly reinforced, right? One row of rebar. Hey, couldn't get much easier than this. One row and you're done with it, right? So how difficult can that be, right? How difficult can that be? So be careful here. Be careful here. We are going to show you what if we have multiple layers. What if we have multiple layers? Okay. So now example 2. Okay. Example 2. Okay. We have multiple layers. Okay, multiple layer, but still called singular reinforced. I have a question. I know. Just give me 1 second. Okay, singular reinforced section. Okay, so let's go over the chat to see any question comes up. Could you go down? Could you go back to real quick? Go back here. Even more. Example 1 here, here. Did you catch it?
It's not currently showing right now.
All right, let me do that again. Sometimes the screen freezes. Okay, I have to stop sharing and reshare. Give me 1 second, okay, folks. Hope it won't be a technological barrier today. All right, so let me try it again. Oh, craps. Give me 1 second, okay? Something's wrong, I feel. Stop sharing. Okay. Okay, here. Okay, let me reconnect. It will take a second, okay? Okay, this is really annoying. All right, folks, it doesn't seem to work. Just give me 1 second. Let me try to bring out from here, okay? Try to bring out from here. I think I can probably don't need to. Okay, I think this is it. Let me try to do this. You see it. Can you guys see this? Can you guys see the screen?
Yes.
All right, good deal. So I'm trying to project it on my screen from iPad. So let me do this 100 times. Okay, so this is example 1, right? We just talked about this. This is example 1. Okay, right? You got it. If you want to finalize your answer, mn equal to a 240 and phi mn equal to 216. Okay, so this is for single layer. Okay, single layer. All right. So sorry, folks. Let me try to share my iPad again. Okay, let me try to share my iPad again. Sometimes this thing is stupid. Give me 1 second. Okay. All right, folks. My iPad died on me. Okay, my iPad died on me. All right. Let me see if I can do this. Okay. So this is pretty bad. Let me see if I can do this. Stop sharing. Admit. Okay. Let me share it again. One second. Let me restart. Okay. Sure. Usually it never happen like this. The whole semester last time only happened once, I believe. Okay. All right, I think I'm gonna shut it. Okay. All right, folks, seems like I have some technical difficulty today on this continue, but I'm done with my notes. I'm pretty happy. I just want to add more things, okay? So let me try to do this now. I can probably draw here. So second example is going to be example 2, multi-layer. Let me show you my screen, okay, so you can still see it. And again, this notes will be there. So multi-layer. Okay, singularly reinforced. All right, still singularly reinforced section. Okay, analysis. All right, and this is not too bad. Why I'm saying that is, think about it. So I have a section like this, right? I have a section like this. Oh, okay. Now without my iPad, it's gonna be horrible, but just bear with me, okay? Let me finish today's lecture. It's not too bad. Oops. Let's just pretend this is a rectangular section, okay? And now I have bars, right? I have bars, and I'm just gonna use this one. So I have bars here, bar here, okay, and bar here, bar here. 4 bars, right? 4 bars. And to make it even bigger, I show that this is 1 bar, this is another bar, and this is bar, this is bar. Okay, and underneath I have a line which is edge of the concrete, Okay, and now let me draw this. This is dashed line from the center of the bars, right? And I say if this is 2.5 inch, okay, and assume the distance between the top row to the bottom row here is 2 inch. All right, just assume here. I'm just making assumption here, 2 inch, okay? And let's even assume these are all number 9 bars. Number 9 bars. Okay, so the only thing that you need to pay attention to is that when I trying to find the depth of the section, okay, when I'm trying to find the depth of section, remember we said there are two definitions of depth. One is called ds, which is the depth of the group of the bars. Okay, remember this is called ds, which is the depth of the group of bars, meaning that you need to find the centroid of these bars. Need to find the centroid of these bars. Okay, so our next job is how to find the centroid of the bars. How to find the centroid of the bars. Okay, so that is the difficult problem, right? That is the difficult problem. So let me try to bring out the screen again, see if this works or not. Sometimes it just bugs me. Sometimes it just this problem. Okay, so let me try to go back and share my screen again. Okay. Okay. Come on, it gotta work. All right. Okay, this is really annoying. Okay, now, all right, no more let me working okay on this. So stop sharing, go back to this screen. Okay, I can still show you how to do this. So now with this, right? So how to find the centroid of this, right? So assume this distance here from the centroid of the bar to the bottom of the bar is y bar. Okay. And how do we find that distance, right? So essentially y bar will equal to the summation of area of each row, ASI, area of each row, multiplied by the distance of that row to the reference line here. Where the reference line here? This is reference line, okay? Bottom line here is reference line. I'm sorry for this wiggling behavior, okay? It just out of expectation today, but this is the reference, okay? So meaning, for example, the first row, D1 would equal to what? This is the distance here. So D1 in this case equal to 4.5, okay? 2 plus 2.5, right? So this is 4.5 inch. And D2, which is the second row here, okay, that is essentially 2.5, 2.5. And summation of this divided by the summation of all the area of steel, ASI, and get you the distance, Y, which is a group of the bars, okay, which is the group bars. So let's calculate out, okay? And so this simple calculation, so bear with me, okay? I just want to finish this. That's our plan today. So Y bar for this, right? A1, D1, okay? This is annoyingly slow, I know, but let's try to bear with me just for a couple minutes. And this is A2, well, you know what? Well, anyway, this is plus A2, D2, okay? And now divided by A1 plus A2, okay? A1 plus A2. All right. So you notice that I'm assuming number 9 bars. You notice that I'm assuming number 9 bars. So happen to be that for number 9 bar, each bar have an area of 1 inch squared. 1 inch squared. All right. So you say, Bob, you know, how does that affect me? You know, besides that your ugly writing, how does it affect me? Well, it actually affects us quite simply. I have 2 bars, right? In the first row, D1 here. So I suppose have 2 inch squared. So just 2 inch squared multiplied by distance of D1, 4.5. You see, it's very easy. I love number 9 bars, okay? That's why it says very important to you because I love it. So I use that in the exam as well, okay? In the exam as well. So to speed up your process, whenever you see number 9 bar, that's 1 inch squared, okay? And A2, which is the bottom bars, right? So I have another 2 at a distance of 2.5, 2.5, okay? And the total area of steel, I have what? 1, 2, 3, 4, total 4 bars, so 4 inch squared. And that is my center of the group of bars. Okay, so quickly, this is 9 inch, and this is 10, this is 5. Actually, this should be 5 inch to the power of cube anyway, divided by 4 inch squared. So let me just make sure the unit don't mess up. Okay, so let me take out this inch. This is wrong unit, okay? Just use the number, numerical number, okay? So bear with me, we're almost done with this one with my ugly writing as well. And 9 plus 5, that is 14, and divided by 4, so that is 7/2. So you got what? 3.5, and now this is inch, okay? 3.5 inch. That means this number here is equal to 3.5 inch. All right, okay? It said, Bob, what's the big deal? I got a group of bars, center of it, and the distance between the center of this group to the bottom layer is 3.5 inch. So what's up? Now, what's up is that I have a height of the section is h, right? And I'm just gonna give some numbers, say h equal to 20 inch, pretty regular number. And with this y bar, I can directly compute the s now. The s, which is the depth of the group of a bar, equal to h minus y bar. So that is 20 minus 3.5. What I have? 16.5, right? Man, I feel like I'm going back to kindergarten. And I swear to God, I draw better when I was a kid than this. But anyway, sorry for that. Again, the depth of the group of bar is 16.5 inch. All right. But the last layer, dt, which still is right here, okay? Last layer dt is right here. And that dt equal to h, which is 20 minus 2.5 inch. So last layer dt is different, and that is 17.5 inch. Oops, 17.5 inch. Apologize, this is 17.5, okay? 1.7. So what I'm trying to say is that the difference between multi-layer reinforced section and single layer reinforced section is that in single layer, ds equal to dt. In multi-layer, they're not. So when you check for strength reduction factor phi, remember phi, you are going to use epsilon t. So they do not equal to epsilon s anymore. Does not equal to epsilon s anymore. So don't do that, okay? For multi-layer reinforcement, and that is the sole difference, okay? That is the sole difference. All right. Okay. Now I'm done with today's lecture, and thank you so much for accommodating on the last part of the ugly drawing due to technical difficulty. And I'll clean this up before our next lecture. You should see a cleaner version after you're done. Okay. I'll upload the cleaner version to the file folder. So double check with your writing today and the cleaner version. If there's any discrepancies, please email me. Okay. Please email me. I see a chat question. Thank you, Professor. Oh, thank you. Okay. All right. That's all for today. Feel a little bad at last minute. We have to use this doodle drawing, but most of the content will cover. If there's any question, let me know. Considering that you're doing, thank you. Yeah, appreciate that. All right. Any other question for me, guys? Now, this is very important stuff. If you have any question that is unclear about this procedure, you need to ask me now, okay? Anything? Anything? All right, okay, so seems like a lot of digest, all right? I'm gonna stop here, and please make sure you understand the whole procedure, okay? Understand the whole procedure. And today is Thursday, so I'm going to leave the first homework. You can start, but you won't be able to finish because we haven't covered the multi-layer. We'll finish multi-layer on Monday, and you'll be able to finish all the homework on Monday, okay? But do start looking at your homework right now, okay? Don't delay it. All right. Now, I remember one of you have a question on the homework number 1. So please stay behind. And if anyone have a question, also stay behind. If nothing else, I wish you a good weekend and see you on Monday. Okay. And don't forget, homework is due today. Okay. Homework is due today. Thanks.
All right, I got my question for you if you're ready for it.
Yes, sir.
So I was working with number 4 and I was talking with one of our other classmates, and